So, welcome back guys, and I do hope as ever you and your family are keeping well. So we're going to continue our study of gravitational fields, and what we're going to look at today is satellites and the sort of maths and physics behind those. So firstly, let's look at what a satellite is. And it might surprise you that the term satellite just means something orbiting something else. So what about this? What about the moon? Well, the moon is a satellite. It's a natural satellite of the Earth. And of course, we are a natural satellite of the sun. But I want to take this a little bit further and look at something that happened back in 1957. So back in 1957, the Americans and others were pointing their antennas up at the sky, and they heard this beeping, this sort of beep, beep, beep. Now, I'm sorry, I wasn't around at that time to hear it as well, but it must have been something quite special. The first time a signal had been heard from out in space that was sort of regular and repeating. And this was Sputnik. So, October in 1957, October the 1st, the Russians had successfully put a satellite into orbit around the Earth, and they'd made it. So, this type of satellite we'll refer to as a man-made satellite. So, what I'd like to do today is to have a look at the physics behind where we put satellites, how they orbit, whether they need motors to orbit, and what they're used for. So I hope you've got a good understanding of Kepler's laws from my previous films. And satellites must obey Kepler's laws, just like everything else that's orbiting out there. But one of the things you'll remember about Kepler's laws is that the orbits are slightly elliptical. Now, in the case of the satellites we're going to look at first, the orbits are almost completely circular. So, to make the maths and understanding a little bit easier, we're going to assume that the orbits are perfect circles. Okay, and that will lead us to some interesting physics. So, if you remember firstly, if you swing something around your head, or a car goes around a circular radius, circular corner more correctly, okay, of fixed radius, there's a force that needs to be applied to hold it inwards, and we call that the centripetal force. And it's really important that you remember that the centripetal force is equal to mv squared upon r. So the force pulling a satellite inwards will be equal to mv squared upon r. And that force on the satellite, is caused by the gravitational field of the Earth. I mean, more correctly, the combined gravitational field. Okay. Now, what's interesting is this is the mass of the satellite. This is the velocity squared of the satellite, and that's the distance, remember, not from the surface of the Earth, but from the centre of the Earth, assuming it's a point mass. But we know something else. Not Kepler now, but Newton and Newton's law of gravitation. We know the force of gravity at any point away from a point mass is G m upon r squared. Okay, so let's just remind ourselves what these letters are. I've left the minus off for the time being, okay, because we're going to get minus r's in both sides. The gravitational force constant, that very, very small number. The mass, it doesn't matter which way around these are, but that m is the mass of the large thing, so that's going to be the mass of the Earth. That's going to be the mass of the orbiting object, so the satellite, and we know what r or r squared is. That refers to the distance from the centre, I keep saying it, not the surface, the centre of the point mass. So what we'll do is we'll take this formula a little bit further, and we'll see what v has to be for the satellite to stay in a stable orbit. But first, let's talk a little bit from GCSE and use it in the A-level maths here. It's never a good idea to forget some of the GCSE and even some of the fairly simple formulae which do get used at A-level. When you look at F, okay, in a mechanical system, when you look at F, always think F's that are unbalanced, if there's a resultant force, cause acceleration. So, of course, you remember that F is equal to ma. Sort of slightly incorrectly, but called Newton's second law, but it's bound up in Newton's second law, that if an unbalanced force acts, the object will change its velocity. Okay? Now that's interesting, because if the mass of the satellite is constant, which indeed it is, and we put it in a circular orbit, r will remain constant, then the force on the satellite will remain constant, okay? Which means that the acceleration of the satellite will remain constant, okay? So all of these numbers stay the same for a satellite in a circular orbit, okay? So this is going to remain constant. Okay, now, if that's not the case, its orbit will be different from circular, or it'll be unstable and the satellite will either crash into Earth or it'll go flying out into space. So let's look at what this means in a little bit more detail. And bound up in this equation is something that most students find really difficult to get their head around. That if there's a force on the satellite and it's constantly accelerating, then it must be getting faster. Okay, well that's true, but it's getting faster in some directions as rapidly as it's getting slower in others. Okay, so I haven't explained that very well. If you know what I'm talking about here, it's easy. But what you've got to remember is a satellite doesn't orbit in a straight line around the, shall we have circular or spherical Earth. What it does is it falls inwards. So it's heading off in this direction and falling in, heading off in this direction and falling in, heading off in this direction and falling in. So it's in a circular orbit. So it's constantly changing its velocity. For GCSE students, I like to point out that it's heading off at a high velocity in this direction, and then the brakes have been put on, as it were. Okay, the force of gravity has pulled it such that later it's now moving in this direction, which is a negative velocity. So that force will be causing a constant acceleration and therefore a constantly changing velocity, but no change to the speed. So that's how we explain that something can be accelerating but not speeding up. So there you saw the proof that I can't talk and breathe at the same time and write. I've corrected Sputnik's name. Sorry for that one. Okay, so let's now have a look at this equation here and see if we can prize out of it the velocity that a satellite has to go at to stay at a stable orbit, at a fixed radius from the Earth, or if it's us around the Sun. Okay, so we've got mv squared upon r. So that's the centripetal force on the satellite. I know I'm repeating myself, but you can get confused about what all these letters are. That's the mass of the thing that's orbiting, so that's the mass of the satellite. And we know that that's equal to g, the mass of what it's going round, multiplied by its mass, divided by the distance from the centre of the point mass that it's going round, assuming the satellite's a much lower mass, so the centre of gravity, as it were, is right in the middle of the object it's orbiting. Okay, well, you can see that we've got some terms here that are on both sides of the equation. So we can say that v squared is equal to, okay, so here's our g m, little m, upon r squared, and then the r comes up here. And what's interesting is the mass of the satellite goes down there. Okay, so let's take that a bit further. The mass of the satellite goes, okay, that squared goes, and so does that r. So we're left with v squared is equal to g, mass of the object that is being orbited, divided by r. So the velocity that it will orbit at is equal to gm upon r square rooted. Okay, so that's really interesting, and it might surprise you that when something orbits another object, so when a satellite goes around the Earth, the velocity that it has to go at has to be fixed to give us that r. Okay, it's really important, this, because the gravitational constant is going to stay the same. The mass of the object it's orbiting, the Earth, is going to stay the same. So if we want to position a satellite at a particular place, we have to give it a particular velocity once it's off on its orbit. So it has to be, when I say launched, that might actually be sort of turfed out of a rocket at its orbital radius, but it has to be put in orbit at a fixed velocity to give it the position of orbit that we want. So think about what this means if we want it to orbit closer to the Earth, okay, and what happens if we want it to orbit further away from the Earth. So you can see there's a sort of inverse relationship here. So the further away you go, okay, the slower the orbit's going to be, and the closer you go, the faster the orbital velocity will be. So now let's have a look at the uses of satellites. And I mean particularly here man-made satellites, okay, those ones that are launched by space agencies from around the world. Without wanting to go off on too much of a tangent, there's a bit of history here. The moon, the natural satellite of the Earth, has been used for communications. Back in the day, radio amateurs and people like that realised that they could take their antennas and beam radio waves and microwave radiation up at the moon, and it would bounce off, and maybe it would go a bit further around the Earth. It would sort of see round the Earth's curvature. But I'm going to talk now about satellites that we've launched, okay, man-made satellites. So they're used a lot for communications, okay, satellite phones, things like that, satellite TV, etc. Again, there's a bit of history to this, and I'll do this quickly. Some of you might know the BT towers in London and in Birmingham. And when I was younger, they were absolutely covered in dishes, which were part probably of satellite communication systems. And if you look at the towers now, the dishes have almost completely gone. One of the reasons may well be that we are communicating via phone, well, we don't use satellite phones, do we? But via phone and TV using fibre optic cable now under the ground. And if we talk to America, we might well be talking on a transatlantic cable that runs under the sea and is fibre. Whereas back in the day, if you made a call to America, there was always a bit of a delay, that really weird delay, because you were using a satellite link and the signal had to go all the way up into space and then come all the way back down again. Okay, so these are very common uses of satellites, but there's one that just doesn't seem to be going away, and that's used by the military. Okay, well, it's a bit difficult to get information about what the military are using their satellites for, and they seem to be launching more and more and more. You often don't even hear of the payloads that are on some rockets. I seem to remember when I went to see the space shuttle launch many years ago, that it was doing space science, etc. But I think there were also other undisclosed packages on board. And the military, I'm sure, are using their satellites for lots of very, very good things. But I'm going to write here spying. Okay. Now, should we put that down as observation? Okay. But it's quite important when a war's on that there are some communication links, and also there's some good photo reconnaissance, and satellites are brilliant at doing this, especially if they're close to the Earth and have very high resolution cameras on board. Okay. Another really, really important use is Earth observation. Okay, now this is really important for looking at the Earth in terms of, particularly for us, things like weather. We get a lot of our weather data from satellites. You might have seen satellite pictures of these great big huge swirling masses of air in America when they have sort of really, really strong winds and sort of tornadoes and things like that. Okay, so we can predict how the weather's changing. At the moment, it's a really interesting time with us all in sort of lockdown because satellites are being used to look at global pollution and things like that. And I think there's been a real change due to power stations shutting down, big business shutting down, and the reduction of road traffic. There is one satellite that I'd like to mention which isn't observing the Earth, but that's the Hubble Space Telescope. So we can put satellites up in orbit and point them away from the Earth and get incredible pictures of objects within our galaxy. And currently this one is being used, but the James Webb Space Telescope is the one that's being built at the moment, and I think it's been held up yet again. But that will be taking even better images way out into the depths of the universe. And finally, one that we all use, and I like this one because it was unheard of when I was a kid, and that's GPS. Okay, now there are a series of systems that you might recognise as GPS, but the Global Positioning System is a particular one. But shall we say using satellites to give us an indication very precisely of our location on the Earth's surface. And this came about when I was a bit younger, and there was a lot of talk in scientific papers about how this could be used. Again, you can Google it if you like, but this one goes back to the military, and the GPS satellites weren't available to the public at all. The receivers were very huge and heavily encrypted, and as equipment got smaller and smaller and smaller, the American government had the good sense to reduce a bit of the encryption on GPS so you could get a reasonable location. It wouldn't allow you to fire a missile accurately at someone else, but that's perhaps not what you were thinking of at the time. And again, if you Google it, there were some natural disasters that happened, and the American government very sensibly decided to remove the encryption on GPS, which allowed the general public to get much more accurate fixes, and of course the emergency services. But there are other GPS systems using satellites orbiting the Earth, because what if the American government decided to turn it off tomorrow? Yeah, we can't be too reliant on one positioning system. So the Europeans are putting up another one, and I believe the Russians are as well. Okay, so there's some use that we put satellites to. So what we'll do next is we'll look at what types of orbit, what shapes of orbit, what positions of orbit we need to put satellites in so they're useful for us. So let's now look at 3 distinct orbits that we're going to put satellites into. And I'm going to try not to go off on a tangent, because I did a little bit of work when I was younger on satellite imaging, and I could talk for hours about it. So let's start off with low Earth orbits. Now, what I mean by a low Earth orbit is it's going to orbit quite close to the Earth. So I'll keep the diagrams very simple, and we'll see how my drawing skills get on here. But if you remember, the velocity of the satellite is proportional to the square root of 1 over the distance from the centre of the object it's orbiting. Okay, so as this gets smaller, as we get closer, this is going to get faster. So if we put satellites in low Earth orbit, they're going to whiz round quite rapidly. They're not going to take many minutes to orbit the Earth. Okay, so here's the Earth. I'll just put the poles there to keep it simple. Okay, and we'll have our satellite orbiting the Earth, and it's going to be in quite sort of close orbit to the Earth. So round it goes and back the other side. Okay, so you'll notice that this orbit is not around the equator. It's not polar, but it's tilted, and it's whizzing around the Earth, not taking very long at all to orbit the Earth. Okay. Again, this is not really detailed for A level, but it's in its descending orbit here. Okay, and it's ascending behind, if that's the north and that's the south of the Earth. And it's good to keep in mind where the equator is. Okay, so these guys are fast, yeah, they're in close, and these are very good. I'm not going to say spying. These are very good for observing the Earth. Okay, you can use cameras on these. They have quite large lenses and they're high resolution, but they can get pictures quite close in. Absolutely brilliant for Earth observation. Okay, so the next one we'll look at is the polar orbiter. And this one, the hint's in the name. Okay, so here's the Earth again, north and south. Let's not forget the equator. Okay, and what this one does, which is quite clever, is it comes up from behind the Earth, over the poles, and back again. So let's do that and that. Okay, and I'll label north and south there. Now you can get into a bit of a stick with this one because you think, well, what's the point of being over the North Pole and the South Pole? I'll come to that in a second. Okay, but the really interesting thing about this satellite is it's at 90 degrees to the equator, and that orbit is where it's been put. So that's the orbit that it has. Okay, it stays. I suppose if you can imagine it sort of coming towards us and then going away, and coming towards us and going away. Okay, but here's the really clever bit. Okay, the Earth is rotating. So, quick change of memory card there as my camera beeped at me. So, perhaps I'm talking for too long. So, I was just saying that the Earth is rotating with the polar satellite. It stays in the same orbit and the Earth rotates underneath it. And it's at this stage, I always ask my students, especially you guys if you were here, I'd say, how long does it take to image the whole Earth? And people think about it and go, yeah, okay, this side and then that side, and the Earth rotates. 24 hours, yeah, that's one rotation. And you're wrong. Okay. If you think about it, if this side is daylight, it's getting daytime here and nighttime there. And then the Earth will rotate 180 degrees and it will get our nighttime and the other country's daytime. So in fact, with its orbit, it only takes 12 hours to image the whole Earth. Okay, so it's quite a clever satellite. And this is one I did quite a lot of work on, but you can see that it's moving very quickly. And if it's moving, it has a disadvantage for those of us who did satellite imaging, that we can't point our antennas at it, okay, because it's whizzing overhead. Yeah, think about where it's going to come from, the north, and go to the south. So if that's north, then we had to point our antennas at north. We had to look up when it was going to arrive, okay, using a set of things called Kepler elements, surprise, surprise, a timetable for the satellite. And then we'd point our antennas at it and we'd track it with our antennas and then it would disappear. Okay, the Earth would rotate a bit and then it would appear sort of over the horizon, but we don't need to worry about that. But do you see what's happening at night time? It's coming from the south. So our antennas were over here and then we could get ready for it to come and then move the antennas this way to get the other orbit. It's an ascending orbit here. Okay, and the satellites I work with would have switched on their infrared cameras, so we'd be imaging the Earth in heat, so we could see something at night time. And it was particularly interesting when there wasn't cloud cover, because you could see cities and towns and things. Partly you could see the light, but you could also see London was much, much hotter than other regions. Okay, so quite close to the Earth. covers the whole Earth's surface. Brilliant again for imaging. Okay, and the satellites that I was looking at would image the whole of the UK in sort of one lens slot. It wasn't, I wasn't looking at car number plates or something. The cameras on them produced a sort of UK image and a little bit of Europe as well. Okay, so there's one more orbit I'd like to add to the list, and this one is a very special orbit. It's called the geostationary. The geostationary orbit. Okay, and this one is very, very clever. Again, there's history to everything. I haven't looked this up in extreme detail, but I believe Arthur C. Clarke, was he the 2001 A Space Odyssey guy, who wrote a novel about throwing something up into space and it orbiting the Earth. And he came across this kind of idea, what if it orbited the Earth? What if it went round the Earth? Not every 100 minutes, which these were, okay, but it went round the Earth every 24 hours. This is really important for A-level, okay? So it had a velocity such that it went round the Earth every 24 hours, which means that we have to put it at a specific radius away from the centre of the Earth. So let's draw it first. Let's try and draw it first. So here's the Earth. North and south, equator. Okay, and there are lots and lots and lots and lots of geostationary satellites. Okay, they are all taking 24 hours to go around the Earth, so they've all got the same velocity, and therefore they are all at the same radius, which means the geostationary orbit is quite cluttered with satellites, and they're all around the equator. Okay, so these satellites, get my pen to work, these satellites orbit the Earth around the equator. Don't think I've drawn that very well, but you have to sort of imagine coming out from this diagram. Okay, so let's have a look at this in a little bit more detail. Do you remember that with this satellite, we had to move our antennas? But with the geostationary satellite, we can position our antennas on the equator and look up, and if the Earth goes round once every 24 hours, okay, and the satellite goes round once every 24 hours as well, then the clever bit here is, as the satellite whizzes round to go round once a day, and the Earth does the same, then the satellite will stay over exactly the same point of the Earth at all times. Geostationary. It's quite a nice example of sort of relative motion, this, that the satellite's going fast, the Earth's going slower but still going fast, but when you look up from the equator, okay, the satellite doesn't appear to be moving at all, because it's going overhead as rapidly as you're rotating sort of away from it, as it were. Okay, so it stays overhead, which means your satellite antennas can be fixed in position. So you get yourself a dish and you point the dish at the satellite and it will always stay lined up. These are absolutely brilliant for communication systems, large-scale communication systems, Earth stations and things, where we're transmitting maybe millions or hundreds of phone calls up to a satellite and down to another country. We don't need to steer our dish. Satellite TV, okay, there's a slight catch here. I always find it interesting when I go to Africa and places like that, and countries in Africa and places in America where you're quite near to the equator, because if you're near to the equator, contrary to what my diagram looks like, the satellites will be directly overhead. So the dishes sit on the hotel roofs and they point straight upwards. Whereas in the UK, if we're over here and we're having to look at a geostationary orbit satellite over the equator, we have to tilt our dishes at an angle to see them over the equator. And I always say to my students here, if you were to drop me off in the middle of nowhere I'd use quite a few clues to work out where I was on the Earth's surface. But if I was in a town or a city, I'd go looking for satellite dishes. And I could work out my position on the Earth's surface up or down, so latitude, okay? I could work out where I was from the angle of the dishes. It's worth saying here that if you're in countries that are very polar, so you're up in Norway and places like that, the horizon is kind of going to get in the way. Your dishes are not going to point up, they're going to be trying to point at the beyond the equator, above the equator, and the curvature of the Earth might sort of form a little bit of a shadow or similar things like that. So satellite TV is not as effective out there. They would use local links, or they would use fibre optic cables. Okay, so a very clever type of satellite this, brilliant for communications and also good for Earth observation. There's a catch. I've used these. The catch is that whilst they always stay overhead, you can always pick them up with your dish, so you can get images anytime you like, day and night. They will only image that bit of the Earth that they're positioned over. So there are loads of these over America, over Central Africa, over Asia, almost none, well, when I say none, very few over the Atlantic or the Pacific. The other thing is, because they're very far away, the image you get as an amateur like me, okay, is a very large area. You could see the whole of Europe, etc. And as you zoomed in to the image, it became very pixelated. But it's one that comes up a lot at A-level, so it's good to really understand what the geostationary satellite is. So now let's look at a problem that comes up quite frequently at A-level. How high would we have to put a geostationary satellite at to orbit the Earth and make sure it's geostationary? Remember that means that T, capital T, the time period, is 24 hours. Okay. Now, again at A-level, lots of catches here. Remember height, so that means above the Earth's surface, and the time period is in hours, but of course we do everything in seconds. So, where do we have to put it? At what distance will it be above the Earth's surface? So I've redrawn the geostationary satellite, rather better there. Okay, and it's a bit small, but I've drawn a dish on it, and I've shown that beam coming down from the satellite. And it's interesting, you'll see that the beam spreads out, you get some diffraction, and also it has a sort of area on the Earth's surface that it covers, and that's what we call the footprint of the satellite. So clearly this satellite has a footprint here, but not on the other side of the Earth, or on the poles for that matter. Anyway, we're losing track of what I'm meant to be doing here. So how high does this satellite have to be positioned above the Earth's surface to be geostationary? Well, firstly, let's remind ourselves of Kepler's third law. Okay, so you should know these laws off by heart, but it was a mathematical relationship that the time period of an orbiting object is proportional to, well, the time period squared of an object going around the Earth is proportional to the distance from the centre of the thing it's orbiting cubed. Okay, so let's state that in a more full way. So t squared is equal to, and then it was quite a complicated bit, 4 pi squared over gm, all in brackets, r cubed. Okay, obviously you don't need the brackets there, you can put the r cubed in here, but there is your t squared is proportional to r cubed. So what we're going to try and prize out is what's r going to be. Okay, and then we need to remember that that isn't the height of the satellite, that's from the centre of the Earth. Okay, so rearranging this one, this is something you'll be expected to do at A-level. T squared G big M, okay, all divided by 4 pi squared is going to be equal to r cubed. So we want r, so we've got to take the cubed root. So r will be equal to the cubed root of t squared gm upon 4 pi squared. Okay, now have a look at this fella. I shouldn't have to say this. Plenty of room for error there, sticking things in to your calculator, forgetting the cubed root, or dare I say, some people not even knowing where that button is on their calculator, getting things in the wrong units, particularly that one. It's not the number 24. Okay, so what I'd like to do now is work out where do we need to put the satellite for it to be in a geostationary orbit. Right, so I put some data on the screen here that we need to do the calculation. So we've got the radius of the Earth, and should I say kilometres? So have a think about that one. Okay, mass of the Earth we've got, the gravitational constant, that very, very small number, and the time, hours, guys. Okay, so can you pause the video now? Yep. Maybe pause it on this screen, or I will take a screenshot of this in a second, so maybe pause it on a little bit later on. Okay, and can you now do the A-level calculation? Okay, at what height does a geostationary satellite have to be above the Earth's surface to make sure that it's geostationary? In other words, it has a time period of 24 hours. So I wonder how you got on. So there's our formula, and I'll just point out that in this formula that the mass is the mass of the Earth, so the mass of the satellite is irrelevant. Okay, they range in masses between a few kilograms, quite a lot of kilograms, up to a few tons. They can be quite heavy objects. But remember that they've got their electronics, they've got their solar panels and their batteries, but they don't have a great big rocket motor on them because they don't need any motors to orbit. Yeah? Remember, they would be heading off into space, and it's the centripetal force, the gravitational force from the Earth, that keeps them orbiting. And a lot of students, particularly GCSE students, really struggle with that. They think they've got some kind of engine that drives them around the Earth. And of course, how would you refuel it? Yeah, especially at the distance that we're going to calculate. Okay, they will have very small thrusters on them, but that's just to give them slight changes in orbit if they're not quite in the right place. Okay, but they certainly don't use those to drive them around the Earth. Okay, once they're up there, they're in free fall, aren't they? Okay, they don't need motors. So let's stick some numbers in. So let's get our cube root. I nearly said square root. Let's get our cubed root sorted there. Okay, and maybe in an exam you might want to highlight that or something. Do lay out your working. Okay, don't just do it on your calculator. Right, time period squared, got to be in seconds. 86400 seconds squared. I think that number is given on the formula sheet if I remember rightly. Okay, times by g, 6.67 times 10 to the minus 11. Okay, times by the mass of the Earth, 5.97 times 10 to the 24. This is all in the right units. And then we divide that lot. Going to need a ruler to do this. Okay, by the constant number of 4 pi squared. Okay, so I hope you got this answer. So the radius of orbit. Okay, I'll just switch pens. They tend to dry out a bit, these fellas. Okay, the radius of the orbit will be equal to 4.22 times 10 to the 7 meters. Okay, make sure you always make the decimal point clear. And always use a decimal point, guys, because my overseas students use commas, and that's a bit confusing. Use a decimal point. We won't go into mad detail about how many significant figures we need at this stage. Okay, but I hope you got that number. But do you remember that that is from the centre of the Earth? But the height above the Earth's surface, if you remember what we've got to do, is we've got to take the radius of the orbit and take away, okay, the radius of the Earth. So we've now got just the height above the Earth's surface. And I'm hoping that if you did this, you got the position or the height that the satellite has to be above the Earth's surface as 36 times 10 to the 6 meters. Now I've put it in those sort of units like that, 36, because I like the 6 here. You know how much, those of you I teach, how much I like engineering notation. So that's mega meters, okay? So you can sort of see that this is 36,000 kilometers above the Earth's surface. So geostationary satellites work very well, but they have to be a very, very long way away from the Earth's surface. So they need quite good transmission systems, often quite large antennas to get the weak signal from them. And if they're observing the Earth, if you remember, from this distance, they're going to see a huge area. They're going to have quite a wide footprint. So finally, let's have a look at GPS satellites before we finish. So the GPS satellites, as you know, are orbiting the Earth, and their positions are quite complex. They're not geostationary. Okay, how do you know they're not geostationary? Well, I don't know if any of you have ever seen those pictures that you can get to show you which satellites you're picking up. Maybe that's a bit dated now, but certainly when I first had GPS, on the screen I'd get a picture of which satellites were being picked up, and then they'd move off the screen and new ones would come in. So they're much closer to the Earth, and they're orbiting in a constellation. Now, constellation in this case means a great big collection of satellites that all relate to each other. Okay, and they kind of fly overhead, you know what I mean by this, and other ones take the place, and your GPS receiver picks those satellites up. So, to show you what I mean by that, here's the surface of the Earth. And as you know, we're going to use GPS satellites to give us an accurate position of where we are on the Earth's surface. So it's a bit of a silly diagram, this, but it'll give you the idea. Imagine that you're standing here, and you're there with your GPS receiver in your hand. Okay, and hopefully it's your mobile phone or something like that. It's not very large. Back in the day, these were great big, huge things that you had to sort of get out of a suitcase and set up with huge batteries. Now, I'm going to position some satellites that are orbiting above us. I'm not representing the exact positions of these. Obviously, this diagram is not drawn to scale. Okay. But if those are our satellites, so this is a GPS satellite, and this is another GPS satellite, and this is another one. Okay, and they're whizzing overhead. I can't quite remember how many are up there at the moment, but I think it's in the order of 30 or so. And they're sending down to us signals, microwave signals. Okay. What you'll notice is those 3 satellites, it looks as if they're going to crash into us, don't they? But obviously you know how far away from the Earth's surface they are because you've calculated that. We'll send a signal to our GPS receiver. And here's the clever bit. Okay. that your receiver picks up these signals and they have in them time-stamped when they were sent. So if your GPS receiver knows the time and this signal arrives late because it's had to travel through space, then it knows where that satellite is in a great big sphere around your mobile phone. Okay. The same applies for this one. The signal will come a bit quicker and this one a little bit slower. Okay. So you remember that speed is distance divided by time. In this case, we can assume the speed of the signal is the speed of light. So c is d over t because it's a microwave signal. Okay. And t is d over c. So the difference in time will be worked out from when the signal was sent to when your receiver gets it. And of course, by using a simple GCSE formula in this case, and I am simplifying, then you can work out the distance, because the distance will be tc or ct, whichever way you want to do that. Okay, so that will give the distance to the satellite. Now, I keep saying I'm simplifying here because, oh my word, I am simplifying. Okay, if you know that distance now, you know you are somewhere on this sort of sphere. If you know this, the same for this one, okay, and for that one. So we've got 3 satellites there, and where those spheres sort of overlap, okay, where the times are correct for each, or more correctly, the distances are correct, that will position you on the Earth's surface. So, if you think about it, in summary, GPS positions you by your receiver knowing how far away the satellite is, okay, from how long it took the signal to get to you. It's a sort of triangulation system. You tend to need a minimum of 3 satellites, okay, and it sometimes takes a bit of time for your phone to pick up the right satellites or your GPS receiver to give a position. Now, I should really end here, but I feel a bit nervous about the fact that I've massively simplified this, okay. Some of you may have heard that GPS satellites don't use this formula exactly. They need to use a formula that has corrections for Einstein's relativity in it. And turning that on its head, the fact that they need to use relativity to get the right position of you on the Earth's surface is good proof that the formula for relativity really do work, that it's proper science, okay? Science in action. The other thing is that the satellites need to know, I'm not tall enough to do this, so I'll go over here, that you're not up here, okay? Because you could be in positions that give the same time differences, but you're sort of flipped on the other side, okay? So all sorts of complicated things go on there to know that you're on the Earth's surface. And if you begin to Google how GPS works, there is one thing that all the textbooks miss. That because light is travelling, or at the speed of light, so fast, so the microwaves are travelling so fast, okay, the time differences are really very, very, very small indeed, okay. And if the time differences are very small, then your receiver must be able to resolve incredibly small time differences. And if all these satellites transmit, shall we say, at the same time, okay, they must all have clocks that are absolutely bang on. They are driven by atomic clocks that will be incredibly accurate to tiny fractions of a second. And so that begs the question, how can your mobile phone, your GPS receiver, act in the same way? It's not an atomic clock, and neither is it sort of directly driven by one. So you might want to Google that, and it's really, really complicated. Okay. Finally, and I'm off on one now, aren't I? The signal could be turned off at any stage. So we can't be totally reliant on the US GPS system. And there are other really interesting things you might look up. On the battlefield, you could spoof GPS. You could produce GPS transmitters, the satellites, that aren't. They're actually on the Earth's surface, or they're other satellites that give the wrong signal. So if the enemy is using GPS, they will get the wrong positional data. Okay, so there's a whole massive load of physics behind how GPS works, and it's really interesting to look it up. But I think here I've done the sort of simplest bit of it to give you an idea of how we get position from different times for the signal to get to us. So I do hope you found that gravitational fields satellites lesson useful. Do go back and look over a few bits and make some notes, and if you've got an A-level textbook, compare it to that as well. Anyway, I'll be doing another lesson on gravitational fields soon, and I look forward to seeing you then.